indicated interest in that. But I ran into this paper. And the results were so amazing. I was like, okay, I'm going to scrap my lecture. We're just going to talk about this. So that was 2 hours ago. So the big confession for today is I read this paper starting 2 hours ago, and I created an entire lecture around it. You might have questions. I might have answers. We're going to try to learn together. I think the results are phenomenal, and they're like just directly in line with everything we've been talking about, so I thought it would just be a big mistake not to cover this paper today. So we're going to do, this is going to be our last one on image GANs, but we'll try to cover some other kinds of GANs coming up next week. So, other business things I need to talk about really quickly. First of all, I sent out a midterm evaluation thing for everyone. Hopefully you got that. I would really appreciate it if you'd fill it out. And you don't have to treat me with kid gloves, like, bring it on. You got positive things to say, great. You got negative things to say, great. Like, I'm very interested in improving this class. This is still essentially a brand new class here at BYU, but it's going to be a really important part of our data science curriculum. And so I really want to make it better. So any thoughts that you have for improvement, I would be really grateful if you take just a few minutes to tell me. Second, we are now transitioning in this class. Maybe you felt the transition a little bit. The first half of the class is sort of laying out the mathematical foundations and fundamental concepts of deep neural nets. And the second half of the class is us going through different examples from the literature and we're just going to start reading papers. And we're going to start talking about them and seeing what we can learn. And there's, excuse me, and there's like 10 million deep learning papers out there. And I know that not everybody in here is interested in all of the same things. And so what I want to invite you to do is tell me what you would like to learn. So if there's a specific topic within deep learning that you'd like to explore more, let me know. Because the rest of the schedule for the semester, like I have things planned, I have papers that I think we should cover that I think capture ideas, but if there's specific things that you want to learn more about, let me know, because there's some flexibility in the schedule, okay? So what do you want to learn? Let me know, and please take the online evaluation. Last item of business. So you all asked about the lab specs. The answer is the lab specs are up. We have working code. We're just trying to decide how much to give you. The Celebrity dataset is available for download, but not from like our Dropbox link. You have to actually go to the website to download it. We're going to try to host it on our Dropbox so it'll make it like one less click for you. But you should go ahead and get started on that lab. Any questions? Yeah. No, okay, go ahead.
When do you think that code will be posted?
Probably really soon, like next day or tomorrow, I hope.
So if I want to work on it tomorrow night?
Yes. It's good that you want to work on it. Okay, that gives me like a deadline, so that's good. Okay.
So not on that topic, but any like news about the final project or like when we should turn in like a idea of what we're going to do on that or something?
Yeah, I was going to have you do that.
Okay.
I'm sorry. I actually kind of forgot that I was going to make that an official assignment. Okay, hold on. Final project assignment. Yes, hopefully you're all going on your final projects. So you should be started by now. I know many of you are, so thank you. Okay, so let's dive in. This is really fun. This is kind of a fun lecture. We're going to, like I said, we're going to just try to learn this stuff together. I invite you to go ahead and pull up the paper on your laptops. I'll show you the paper. This, by the way, is a generated image from their technique. Somewhat on the failure side of things. So the paper is called Large-Scale GAN Training for High-Fidelity Natural Image Synthesis. If you just Google that, you should find it pretty quickly. And this guy, Andrew Brock, so this paper was published last month. So it's like brand new. Apparently, this paper is the result of this guy's internship at Google. It's like 30 beautiful pages. Really just outstanding work. I bet he gets a job. Here's some results. Wow. So these are synthesized. So they're far better than anything I've ever seen before. So these were trained, and we'll see So these are class conditional synthesized images, meaning you give me a class. So I want Afghan hounds, and it generates this. You say, give me islands, it generates this. You say, give me monarch butterflies, you can do this. You say, give me cheeseburgers, it gives you this. Okay, so class conditional image synthesis. Here's a few more results from the paper. High resolution, so these are generated at 512 by 512. He's not doing any sort of progressive generation. So this was the thing I thought was really interesting about the paper. So I showed you that video right at the beginning of our segment on GANs with the faces. And if you remember, the like we just barely talked about this, but the technique that they used to generate the faces was they generated them at low resolution, and they gradually increased the resolution. These guys didn't do that. They're like, nope, we're just going to train GANs like brute force. Okay, so I was really, really, really impressed by these results, and I was like, whoa, what did they do? Okay, so I'll just give you like the really quick answer. The reason it's called Big GAN is because this work was done at Google. And basically the argument in the paper is, if you just make your model much bigger and throw much more data at it and train using a cluster of 512 TPUs, then you get great results. And so I was like, I think, so first of all, yeah, I'm like, only at Google, right? And they said they trained, it only took them like a day to train, maybe 2 days. They said between 24 and 48 hours. And I thought, well, that's great. So if I have one GPU, that would take me 512 days. So it's just unfair. So I thought, you know, this is an interesting point for all of us to consider. There is, I think, an argument for saying you can spend a lot of time thinking hard about crazy Wasserstein loss functions. You can spend a lot of time thinking about crazy topologies. But sometimes you can just like solve a problem with joules. And that's what they did. They just like threw more compute at it and got really amazing results. Now, that's not totally true. If you go through the paper, they did some fantastic engineering. They're using a lot of tricks, although the basic architectural ideas are quite simple. So we'll see that a little bit. Okay, I thought also it would be useful to cover this really, really quickly. So they said in the paper, the current state of the art in conditional image generation achieves an inception score of 52.5 compared to 233 point real data. Big GANs achieve 166. I was like, I don't think we've ever talked about inception scores. So there's this question that the community grappled with really early, which is, how do you evaluate the quality of all these generated images? We can look at pictures and sort of visually assess them, but wouldn't it be nice to be more quantitative about that? So what do? And the answer is, let's assume I give you a pile of data. The inception score is an attempt to formalize two thoughts, and they're right here. So saliency and diversity. So the idea is that a human looking at a big pile of data should see something like for any given image, the human would have a very confident score, like a very confident classification for that image. Like I look at an image of pizza and I know it's pizza. I don't have like it doesn't feel like I have some crazy one-hot distribution over 1,000 things and there's probability mass spread over. It's like, no, I just like it's pizza. Like there's like a spike in my distribution. Okay? Saliency. So it ought to be the case that images have very confident classifications, but if we look over all of the images, all of the classes are represented, so that's diversity. And so the inception score formally is this. So the inception score for a collection of images, represented by this random variable x, is e to the expectation under x of the KL divergence of p of y given x times p to p of y. Okay, so what's going on? So saliency is expressed, so y's are classes, x's are images. So saliency is the conditional distribution of y given x. And so this is, you give me an image, and I have some distribution over its class. And we want that to be peaked. as peaked as possible. But then diversity is, this is actually a typo, I'm sorry, that should be P of Y. Diversity is P of Y, so what does the overall class distribution look like? And what we want is we want a measure of, on average, how different is the score for a generated image from the overall class balance, okay? So we don't just want to memorize, like we want to be confident about any given image. So that's called the inception score. Higher is better. So when you see that in the paper, go ahead and that's what we mean. So it's a relatively simple idea. It's actually not the best measure in the world, but it's pretty good. Yeah, go ahead.
So, what is the standard for? Like it talks about, if you look at a picture, like should have a really high, confidence that it's that specific thing, right? Or like one specific object. Like, what is the standard for measuring that?
Measuring confidence?
Yeah.
Well, so we only measure it relative to the overall class distribution.
Yeah.
Sorry, if that makes sense.
So then what is this? So I can say probability y given x, or like probability y, like what is that value?
Okay, so you give me an x, I give you a distribution over y's, just like we've done. So I've built some neural net.
Yes.
Image comes in, distribution over
So
classes
that's
comes
my
out.
specific question is,
Oh.
whose neural net are we using?
Oh, whichever one we're evaluating.
Okay, so it's not necessarily standard across every paper, but like within their paper when they give it real pictures, then their own neural net scores at 250 whatever.
Yes.
Okay.
Or if you're humans.
Or humans.
So you can also look at human level accuracy on this task. So you give a bunch of real images to humans and you can ask them to classify them. If they get that wrong, you can treat that as noise in the distribution and then you can compare things.
Okay.
So it's like human level baselines that classifiers are usually better at. They're actually slightly better than humans at classifying. Okay, yeah, and so the expectation is over X. So that just means if I average over all of the images, say in a data set, and I ask the neural net to evaluate all of them, on average, how distinct is that distribution from the unconditional or the marginal distribution over classes? Okay, cool. So that, just so you know. Okay, so like I said, sometimes brute force is the answer. This is a page from their paper. It's kind of right in the background section. And I'm including it here because I thought it's captured well the trajectory of the discussion we've had so far in this class. We've been thinking about all of the different ways that we could potentially improve GANs. And so they talk about that. They say, like recent research, modifying the vanilla GAN procedure to improve stability, line of work changing the objective function to encourage convergence. Another line is focused on constraining the discriminator through gradient penalties. That's what we've been talking about with the Wasserstein stuff. Normalization, there's these normalization things. You can focus on the architecture. You can focus on how you represent the class conditional information. Should you do one plot? Should you use an embedding? Or should you do? So the point they're making here is like there's all of these different ways to try to improve GANs. And it's great little overview of kind of the space. But they say, but the really big change is brute force. So they have 3 contributions in this paper. And I just wanted to go through them really quickly with you. So we demonstrated the GANs benefit dramatically from scaling. We trained models 2 to 4 times as many parameters and 8 times the batch size. I thought that was really interesting. We've talked about small batches in stochastic gradient descent. And here they're saying, actually what you want is big batches. So they're using batches that are like 2,000 images. And what they say is that gives us much cleaner gradients, which is important when we're doing this class conditional generation. Then they go through it, they say there's 2 simple general architecture changes that improve scalability. To be honest, I couldn't figure out what they were talking about. So this is a quote from their paper. I read the paper, again, like an hour, 2 hours ago. I could not, they seem to do a lot of things on the architecture side, so I wasn't sure exactly which 2 they were talking about. But then they also do some regularization, which I thought was quite interesting. They're doing this thing called spectral regularization, where they look at the weight matrices that they're learning, and they do a spectral decomposition. So do you guys know what I mean when I say spectral decomposition? Like singular value decomposition or an eigenvector decomposition. You're looking at what's called the spectrum, so you're looking at the eigenvalues. And what they show is they show that the eigenvalues of the weight matrices, or the singular values of the weight matrices, depending on shape, gives you a lot of information about convergence. And you can sometimes penalize the big eigenvalues in the matrix, and that serves as a form of regularization, and they show us that. That's helpful. Here's more detail on what they said about scaling. So I thought this was kind of fun to read because I thought, oh wow, we kind of understand a lot of this, but there's still some things that even I'm just not familiar with that they're doing here. So we explore methods for scaling GAN training. Baseline, we employ the SA-GAN architecture of Zhang. So this is a self-attention GAN. I thought it was kind of interesting. They're doing like an attention mechanism on GANs. so it's like the image, as it's generating the image, it can look at other parts of the image that it's already generated to try to make something that's more globally coherent. Okay, cool. So there's the basic architecture. We'll show it in just a minute. It's pretty straightforward. We provide class information. So again, we're doing class conditional generation. So I'm going to tell you I want a cheeseburger or an Afghan count, and then I'm going to hand you the class, but I'm also going to hand you the z vector, and then I want you to generate. So how do we represent the class conditional information? They're using this batch norm thing, and they hand class information to the discriminator with a projection. I think that just means a fully connected layer. I wasn't quite sure. The optimization settings follow blah blah. They are employing this spectral norm thing. Modification, we have the learning rates. We take 2 D steps per G step. So I train the discriminator twice, then the generator once. Discriminator twice, generator once. For evaluation, we employ moving averages of the generator's weights. So I realized we hadn't talked about this either. We've always thought about training the neural net and throwing away everything but the very best set of parameters. So we imagine we have a set of weights. As we're training, we're adjusting those weights. And when we're done training, those are our weights. But you can do this other thing called averaging. And the idea is that you, instead of throwing away previous weights, you go ahead and you're training your neural net that you're keeping an average, a running average of all of the weights that you've seen so far, except then you decay the ones that are far away in time. So just keep a running average of the weights over time. And so you're essentially averaging the parameters, and that can sometimes result in better performance. So I thought that was kind of interesting they were using that trick here.
So like, you would still step the optimizer, but then like,
Yep.
use the average weights instead of the minimum? So like on your next iteration, are you using the average weights, or are you just keeping track of that for your final model?
I think, so I'm actually not sure. That's a good question. So the question is it that you're always feeding the average, like, is it the average weights the thing that you're taking the gradient of, or is the average sort of off to the side?
Sure.
And the answer is I don't know. I think actually the average is off to the side, but I'm not sure. Maybe somebody else knows.
Why would you be averaging the weights? Like, wouldn't it be equivalent to like average your gradient steps, like your step updates?
Oh, it's a little different because at every time your weights are changing, so your gradients are changing, and it's all nonlinear. And so no, it's like the average of the weights says something about the average of where I've been in parameter space. But the gradient of the average is not the same as the average of the gradients because it's not linear. So it's just different. It's just like it's basically like saying, we know that there's noise in this process, and so it's almost like a momentum thing. But yeah, go ahead.
So you mentioned you decay the values, the contribution of values in far past time. So I mean, the term running average implies it's just a fixed window that follows. So is it a fixed window of a certain number of iterations, or you're actually like intentionally just decaying the contribution of the values of the previous?
So we imagine, so the algorithm is something like this. So theta, so we start with some theta naught, and then we're gonna like iterate, and we're gonna say something like theta at time t equals theta at time t minus 1 plus gradient with respect to theta of the loss with some learning rate at time t. This is normal stochastic gradient descent. But then I think what they're saying is they're saying we also keep this theta hat, and we're going to say that theta hat equals theta at time t, sorry, equals 0.0001 times theta t plus 0.9999 times theta f. So it's not a windowed running average, it's an exponentially decaying average
Okay.
with a very high decay factor. So they're saying we're using a decay of 0.9999. Okay, we use orthogonal initialization. So this is one of the things that we had to code up right at the beginning of class. We've always said, you know, don't do that unless you have really good reason not to. But apparently, this makes a big difference for them. You know, they point out everybody else is using just Gaussian or Xavier initialization. So I thought that was interesting. Also, each model is trained on 128 to 512 cores of our Google TPU. And then they compute batch norm statistics in the generator across all the devices, which I thought was interesting. So anyway, the point is, like, they're using some tricks, but a lot of the core concepts we understand about how they did this. It's just that we don't have that. So contribution number 2. This I thought was also kind of interesting. So they said, we're doing this thing, we're calling it the truncation trick. And I was like, oh, this is interesting, I've never heard of this. But they made the following point. They say, when we think about generative adversarial models, we think of that z vector, and we think, where does a z vector come from? Usually we sample it from something, typically a Gaussian. And they say, and they do a bunch of work to explore what happens if you do different distributions over z's. What happens if you use uniform, or what happens if you use, and they have all sorts of crazy things. It's all in the appendix of the paper. But here they also say, if we're going to do Gaussian, they said, you know, sometimes you get those really weird images. Well, maybe that's because when we're sampling from the Gaussian, we're getting things that are off in the tail of the Gaussian. And so maybe what we should do is truncate the Gaussian. So we'll only keep bits of z that are around that are kind of near the middle. And we can set the truncation level sort of just, it's like a knob. So the more we truncate, the more we get rid of the tails of this distribution, where probably our model's not as confident. And this is a little result from their paper that shows this idea. So the thresholds here are from big thresholds. So this is, sorry, let me make sure that we're all understanding here. So imagine that I'm sampling z from some Gaussian, and you all know that if I have a mean, a Gaussian with mean 0 and unit variance, about, if you get out sort of 1 standard deviation is like 0.6, something like that, and 2 standard deviations is kind of up here, and 3 standard deviations is kind of up here. So they're just saying, look, we're going to truncate this at 2 and -2. So anything that falls outside of that will truncate. Similarly, 1.5, 0.5, 0.04. So the very smallest truncation, they're really, really close to the origin. And what you can see here is, so these are the samples you get when you essentially don't truncate. As you truncate more and more, you get more and more realistic looking samples at the cost of some diversity. But this is a nice little trick because it lets you trade off diversity for sample quality. And I thought was kind of nice. These zombie dogs, apparently, they're applying truncation to a poorly conditioned model. I don't know what that means, but I assume it's something to do with the conditioning of the spectrum of the weight matrices. Okay, finally, contribution number 3. So they said that they, when you're training at scale, when you've got 512 TPUs and they're all going, there's new kinds of problems that you run into. And so they said, how can we predict when our GAN is about to explode? And they do some nice work to show that looking at those singular values of weight matrices are a great way to do it. We're not going to talk about that too much today, but I thought it was some nice work that was inspirational. So here's some interesting things. So they're showing here, this is great. So 128, 256, 512, and then this. So this is class leakage, they said. So what that, I think that means is, we asked it to generate a tennis ball, but maybe the representation of tennis ball happens to be close to the representation of yellow fuzzy chick. And so as the neural net is trying to generate both a tennis ball and a yellow fuzzy chick at the same time, you get this very cute, it's just adorable, really. I was like, this is like giving me business ideas. I can imagine like a super cute little robot. Anyway. But I thought, oh yeah, so when you start talking about generating things with hundreds or thousands of classes, and we'll see in the next slide that they're using up to 8,500 classes, that you get kind of interesting new kinds of problems. Yeah, go ahead.
They see what the dimensionality of their Z space is?
128, apparently. Yeah, so surprisingly small Z vectors that are being somehow exploded into these magnificent images. Yeah, Jacob.
So how do they come up with, how do they determine which those classes are? Are those just, do they just take the 8,000 most common classes?
Roughly, yes. So actually they talk about this right here. So, so this I thought was also really nice. So they initially trained on ImageNet, which we've talked about, but then they talk about this new data set, which I've never heard of until today. JFT 300 million. So you can probably guess. This has 300 million images in the data set. They're all labeled with 18,000 categories. But they point out that the category is pretty long tail. So you have a lot of images for a few of the categories, and then very few images in most of the categories. And so what they said was they subsampled the data set, and they kept only the 8,500 most common labels. But that still resulted in 292 million images. So yeah, so half the classes, there's only 8 million images for half the classes. Of course, that's still 8 times as big as the ImageNet training set. So yeah, this is like 2 orders of magnitude bigger than ImageNet, which I don't even think I have that much disk space. Okay, so, and then, yeah, that, like I said, batch size 148. So this idea that scale matters, I thought was really intriguing. It's of course the only the only research. Sorry, it's the kind of research that can really only be done at Google. It's very unfortunate, actually, that in academia we don't have access to the resources for us really to even kind of do this sort of research. But some people they started thinking about this idea, like, wait, how many TPUs are you using? So he said he uses 512 TPUs, 24 to 48 hours. So assuming that a TPU uses 200 watts, which is not unreasonable, like a GPU, normal GPU uses about 200 watts. So they said he's using, upper bound, 5,000 kilowatt hours, which is the average amount that the American household uses in just under 6 months. So somebody said, like jokingly, the good news is that AI can now give you a more believable image of a plate of spaghetti. The bad news is it uses roughly enough energy to power Cleveland for the afternoon. Yeah. Yeah.
That's like, if you were to try to do that, that's like more than $3,000 an hour. Because it's like $650 or something an hour.
Yeah, it's totally nuts, right? I mean, this is actually a lot of energy. And what I think is even more incredible is when you go through the appendix of this paper, actually here, I've got it right here. You should see this. So they do a really nice job of talking about all of the different experiments that they did. So hyperparameter tuning. We performed various hyperparameter sweeps. Okay, no problem. We swept the Cartesian product of the learning rate through 10 to the negative 5th, and initially, so they're like basically saying we tested all these different settings. We tested all these 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 settings. But if each test takes 24 hours or 48 hours or whatever it is, like actually that's a lot. Like, I mean, it's the sort of thing you just like, it's easy if you're Google, because you just write a script, like, you know, for theta in blah, 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 like kick off massively parallel job, and no problem, right? But but you can also see that here when they're talking about, for example, they carve out these frontiers of performance as a function of like truncation levels and things, and these are all individual training runs. So there's a ton of compute, like it's more than just $6,000 worth of electricity that went into making this paper.
No, I was saying that's if you pay for the
Oh,
GPU
yeah.
usage, it's like $6.50 an hour.
$6.50, you're right.
So it's like
Yes.
times 5, 12 times.
Yes, I mean, I think this was an expensive paper.
I was just gonna add, actually, they're using TPU v3, I noticed, which is actually more expensive.
Oh,
$8 an hour.
$8
If
an
you use
hour.
the preemptive one and you like really got your machine size as small as possible, you could probably get down to like $5 an hour, but it's still like $3 or $4 grand for a day of using
Yeah.
big clusters. So.
Yeah, it's a lot of money. Okay, so let's look at some more results. So I thought this was kind of interesting. So first of all, they point out the following. Because of class imbalance, some classes are easier than others. So fruits, awesome. Cliffs, awesome. Samoyeds, really good. Libraries, really good. People, like baseball players, not so good. French horns, not very good. Jamaican steel drum bands, not very good. So, or I'm not sure what that is. But that's a xylophone. I don't know. It looks like they're in a concert. I'm not sure. Anyway, so the point that they're making is, even though we've got some really nice results, because certain classes have less data than others, those are still hard to model. And in particular, interestingly enough, they sort of say, there's actually not that much diversity in dogs, but there's tons of diversity in people, very structured kinds of diversity. And so I think they're sort of arguing, not only do we not have very much data for some of these other classes, it's harder data to model. Okay, I thought it was fun to see interpolation, some interpolation experiments. So now this is a class conditional generator, so you get both a Z and a C vector, and you can interpolate them both. So what they're saying is pick a Z and a class, say, what's that, manta ray maybe? Dolphin crab? I'm not sure. Some underwater aquatic animal. We're going to call that a manta ray. Pick a Z, pick a manta ray thing, but now, because you can interpolate in the C vector space as well as the Z vector space, you can pick, I don't know what that is, what kind of hound that is, some other dog, and you can try to interpolate smoothly in both class and Z at the same time. So I think the results are, this is, I thought, pretty good. The Pomeranian to the robin. I mean, if you have to interpolate like that, I don't think that's so bad. Skunk to, I don't know, I'm so bad at it. Does anybody know what kind of dogs?
Charles Spaniel?
Charles Spaniel?
Wrong
Okay.
color.
Okay.
Maybe, I don't know.
Blue, some sort of, I don't know, blue jay to mosquito. Yeah. Black swan to robin. Cocker spaniel maybe to something. Anyway, the point is, like, I actually really liked these interpolations. I thought they were pretty compelling. And Jacob and
Well, I was just noticing that like a lot of the classes, like Jamaican steel drum band, like that's a very specific class. First of all, have they done a lot of like class-specific generated images before?
people have tried, but the results have never been this good.
Because I'm just thinking, like, if you have something more hierarchical, rather than trying to teach your network to generate like a Jamaican steel drum band, tell it that there are Jamaicans that are humans and they have steel drums and they're a band. Like, if you have like kind of subclasses, do you think that can make this easier to train?
Yeah, so I don't know how they're representing the classes, and I don't know how. I do know that they are doing a hierarchical generation. I'll show you that in just a second. Many people have tried different kinds of hierarchical generation. I think your intuition is right. It's like, yeah, you somehow want to help the network, but I mean, I'll show you what little I know about what they do. But I know that it's hard. Yeah.
So it probably gives a compelling time to like re-illustrate the Animorphs series too.
Totally. Yeah, totally.
So
Yeah, you can have a lot of fun. I think it's a lot of fun. Okay, and then I just thought it was also interesting, they have a really nice result in a paper where they kept the Z constant and only interpolated in the class space. And I thought, yep, looks good. So you've got dog to mountain, you've got dachshund to lynx. I'm not sure what that is. Yeah.
To rotisserie chicken?
This is like shrimp to rotisserie chicken. I'm not sure what this is. Anyway, I don't know. Maybe it's a steak, ginger root, something. And and then dog to bird. Yeah. So again, I think pretty nice interpolations, if you ask me. I think they're pretty compelling. So the benefits of scale. So I thought it would be fun to take a look at their architecture just a little bit. So as I said, Z vector only 128, which is surprisingly, I think, small. I wouldn't have expected you to be able to generate this diversity of stuff, but I guess 128 dimensional space is actually pretty big. Fit a lot of stuff in there. So their architecture looks something like this. You have the class information, which is being fed into these residual blocks, and then you have the Z stuff. And notice that they're splitting the Z vector into different pieces and feeding it into different layers of the hierarchy. So this is kind of what you were talking about, Jacob. This is not a semantic hierarchy, but it is saying something about how parts of the Z vector are going to control low-level features, and parts of the Z vector are going to control high-level features. And those are going to combine together. And so, in principle, since we know how we split the Z vector up, we could say something like, hey, let's just interpolate in low-level feature space, or let's keep the low-level features the same, but interpolate only in high-level feature space, or something like that. And they didn't do that, but I think it would be kind of cool to fill with that. Yeah.
It looks like they're sampling from Z space with the normal.
Yep.
But in our example, we're doing uniform, or is it
No,
like does that make a difference?
I think they.
Or do they all sample Gaussian?
They all sample Gaussian. So I think they concluded Gaussians were the best, but truncated. So they do that truncation trick to improve sample quality. Okay, so then the Z stuff that goes into one of these residual blocks gets split again, and some of it goes up here to this batch norm, some of it goes down here. It's concatenated with the class conditional information, and then you've got some pretty standard other blocks that we know and love. So convolutions, ReLUs, and batch norms. Let's see here, we talked about this. Oh yeah, so I thought you might like to see some failures. So there's, it gets worse, yeah. So I thought it was interesting. You can go check this guy out. He's got a whole series of these, but what I think is interesting here is the textures and the backgrounds look really, really good. And you even have some like clear anatomical details, but something about the global coherence is lacking. And I thought that's interesting. I'm not sure whose fault that is. I'm not sure if that's the discriminator's fault or the generator's fault. But we see it sort of time and time again. So here's, I'm not sure what it is, but it's sort of like if you look at any piece of this, it kind of makes sense. Salamander. Something. On the beach. But like, that's a really good beach, and some cliffs, and like the skin texture, and claw things. A spider with like 12 legs. Another spider. A snake. Kind of like a fully connected body. Eating himself, yeah. A peacock. Something's wrong there. This looks pretty good.
These are just animals we don't know about.
Birdfish, yeah, that's right. Bird squid? Yeah, so again, it's like, wow, you did a pretty good job of putting statistics together, but, and then this is my favorite. I thought this was fantastic. Okay, so One thing I also thought the paper did a good job at, which isn't in my slide because I want to show you again. A very natural question is the generator just memorizing the training data? So one of the ways that we look at that is with interpolations. So if you can successfully interpolate in Z-space, then you can probably conclude that it's not just memorizing things. But another thing you can do is you can ask for any given generated image, what are the nearest images in the training set? Just make sure that it's like not in there. So this is the generated image here. And these images are the 12 closest images if you calculate distance. So what you don't want to do is calculate distance in pixel space. That's a terrible measure of distance. So what they do instead is they use a fully connected VGG16 FT7 features from this layer in this neural net. And they say, let's find the nearest neighbors in that feature space. So hopefully this is a much better representation of the semantics of the image. And so you can see they're all